All right, guys, I'm going to do a few examples off the application packet. Again, I set up a little bit of problem number 1. That should really be a review of what we did yesterday. Problem number 2 gives you the K value, so it's really straightforward. And by the way, time is in hours for that one. Number 3 is just like number 1. Number 4 is a logistic growth question, which means something is approaching the limits of a certain population growth of some kind. So we're going to type this in. I'm going to do it by graphing because you have to find so many bits and pieces here that if I just pull up the graphing calculator and type this in, I can find all of the answers using the graph. If you are using an older model calculator, you will need parentheses around the whole bottom and around the exponent. Okay, like that. So we're going to type 300 divided by 1 plus 19. I'd really appreciate it if you were all doing this. E to the negative 0.3x. And then, what are we modeling here? Okay, number of bears as a function of what? What's the other variable? P of t is the bears, t is time in years, okay? So at one point, it says further down in the question here, 30 years out, and when will the population be 50? So you need to go out at least to 30 years. Whoops, I want to leave that one 0. And then the number of bears. Anybody remember doing these kind of equations before? Generally, this top number is what they're going to approach, as long as you have a 1 plus something down here. So the number of bears is probably going to approach 300, so I'm going to put 0 to 350 just so I can see this. Right, when I graph, there's the number of bears versus time. So how will I find what's going on at 0 and at 10 and at 30? I could use the table. I'm kind of lazy. I'm just going to trace. If I go trace 0, I get 15 bears. At 10 years, I get about 154. Is someone else getting these numbers, or did I do something wrong? No. Okay. Then did it ask at 30 years? About 299 bears, pretty close to 300. And then it said, when will the bear population be 50? So the number of bears is y, so I'm going to put in a y equals 50 line and then find that intersection to figure out when the bears will be at exactly 50 bears or roughly 50 bears. I got about 4.5 years. Did anybody else get 4.5 years? And the maximum number, if I trace over, I went as far as 35. Oh, I'm on the wrong line. Okay, here we go. And I'm at 299.8, so I'm thinking it's going to hit 300 bears, right? Any questions about that problem? All right, on the top of the next page is another problem about an exponential function. Notice the bottom is a big old mess here. When you go to graph this, you're going to need some extra parentheses here, and if you have an older calculator here. You also need to replace this number right here with an initial value. You're supposed to do this graph 3 different times, once with a 50, once with a 1500, and once with a 10,000. They were nice and gave us a window here. The reason this approaches more than 300 rabbits is because this is not a 1 plus something in the denominator, it's a 0.05. And if we do 300 divided by 0.05, we get a much bigger number than 300. So, all right, so let's start typing this in. Can everybody do this one, please? Be careful, they're 0.05s. Plus another parenthesis, 300 divided by, what's the first one, guys? How many rabbits we putting on the island the first time? 50? And negative 0.55x, is that what that says? All right, I think I have all the parentheses I need. All right, and again, they gave us a window to use of 0 to 15 and 0 to 12,000. Be sure you get 12,000 in there, not 1,200. I'm not sure why they picked that because, well, I guess the end they put in 10,000 rabbits, so that makes sense. Is everybody getting that shape for the first one? Then what are we supposed to change for the second graph? Okay. So instead of introducing 50 rabbits, we're supposed to put in 1,500 on this island. So I need to insert, which is second delete, a 1, and then back here is 0. Because I really don't want to have to retype all that. Now, the population still grows, but it starts up much higher, right? Okay. And what if we're really cruel and we throw 10,000 rabbits on this little island? Can this island support 10,000 rabbits? Did I get 10,000 in correctly? I think so. If we put 10,000, they have to die off until they get down to what the environment can support. Okay, so our last graph should look like that. And from the graphs in part B, observe that regardless of the initial population, the rabbit population seems to approach a certain number as time goes on. What is that number? Well, we went out 15 years, so if we just do a quick trace 15, what's it approaching towards the end of our graph here? About 6,000? If we scrolled out even further, I think it would get even closer to 6,000 rabbits. So there's a lot of dead rabbits on that third picture, right? All right, we already have done log questions. Did anybody have a question on those? Okay. Which one? 10? Yes. Number 10, yes, Gunther? You are putting in the pH, so you have 3.0 equals negative log of the hydrogen ion concentration, which is X. So how are you going to undo that? Anybody help Gunther out what you need to type on that one? Okay, so you switch the negative over to the other side. Yep. And then that just means 10 to the negative third is the hydrogen ion concentration. And the label on this section is moles per liter. If I could write. Okay, does that help? All right. Then I was asked about 10 and 11. Any ideas on how to use this half-life formula up here to do 65% remains?
Would you do 0.65 times 0.5 x?
If you put it in that spot right there, that's the initial amount.
Yeah, like you
We
get
want
6
65% to be the remaining amount. Thank you.
0.65 is equal to 30.
Okay, if you're going to call that 0.65, then what did you start with? 100% or just 1, right? Which will make no difference to your equation. I'm just pointing out to you that you have to have an initial amount. And so if we divide by 1, we still have 0.65. Then x is in the exponent, so what are we going to have to do? Okay, so the log of 0.65 equals, if I bring the exponent out in front, I have x over 5730 times the log of 0.5. So then I'm just doing some typing on my calculator. The log of 0.65 divided by the log of 0.5. Make sure you close that parenthesis up top there. And that is equal to x over 5730. So what do I still need to do?
Times it by 5,730.
So I have about 3,561 years until that percentage is left. 61.1, I got. Did you round along the way?
Yeah.
That's fine. If you have 62, I'm not going to count you off. Just depended if you round. I did it all at once, so I didn't round it all.
So 11 would be the same thing, or?
With a 0.42, yep.
Okay.
All right, can everybody look at number 12 with me? This is what we're going to do next week. Okay? We are going to talk about ways to find regression and to estimate populations of things, or estimate, doesn't have to be a population of something, but, and we're going to see if it's logarithmic, logistic, exponential, cubic, quadratic, etc. Okay, we're going to find the best regression equation. Lucky for us today, it tells us what to do. So we need to put some data in and then find an exponential regression equation on our calculator. It says to use 0 for 1960, so this is going to be 0. 1980 will be how many years later? 20, and 1990 was 30 years later. So into list 1, we're going to put those 3 numbers, and into list 2, we're going to put these 3 numbers. Now, this is not really very much data on which to base an equation, but at the same time, it's very nice when you're typing it in to only have 3 data points, right? Okay, you need to be in list 1 and list 2 unless you want to have to do some crazy business later.
How do you get the list again?
Stat enter to get to the list. Good question. It's going to be stat enter to get to the list. And then in a minute, it's going to be stat arrow to the right and down to the one that says EXPREG. Go up onto the title and do second delete. And then give it a name that you're missing, like L1, so second 1 or second 2. Got it? You good? She was missing a list.
Well, I am too.
Okay. You go up onto the title here in the far left corner and do second insert, and then you have to name it. So you go second 1 to get L1 or something.
Well, I'm trying to do that first.
To do second 1?
Big second insert, but, you know. Insert.
Okay. Somebody else need help? Does anybody remember how to turn the plot on after we have those 3 points if we wanted to see them? Because we're going to do that next week.
Second sidewalk.
Yeah, second y equals. And then enter to turn it on and make sure you have things picked appropriately here. And then you always have to do your window. I just do zoom 9 for zoom stat. Do you remember what exponential growth looks like? Curves up? Does that kind of look like it could be curving up? I mean, 3 dots is kind of vague. Obviously, we could make a lot of equations that would go through that. All right, so let's go stat, right arrow. Scroll down until you find exponential regression, which is choice 0, I think. Then it doesn't ask us to store this and graph it. So you can just hit enter if you want all the way through this, or if you have an older version calculator, just hit enter. All right, and then we're going to write this equation down. It's a times b to the x, so it's 0.229 times 1.03 to the x. I don't know, I'm rounding randomly here.
X is time.
And x is time. X is years since what was it? 60? All right. So if we did graph it, guys, you are able to store that equation. So it's stat right arrow down to 0. If you wanted to store it, does anybody remember where we stored in Y1, how we do that? It's the vars key over here, VARS, over to the Y variables, function notation, function mode, enter. So now I'm going to store it in Y1. It does nothing different for me when I calculate it, but now if I look at the graph, it's there. The other option would have just been to go into Y equals and type in what I wrote down, 0.229 times 1.03 to the x.
How does that work for the 83? Do I just?
It's the same. Oh, I'm sorry. After you get up on your screen exponential regression, then you have to type second 1, comma, second 2 for list 2, comma, and then vars business. Okay? Remember?
Got it.
Yeah. All right. Anyway, we don't really need this anymore, but to predict the population in 2009, how many years is that?
49.
Okay, 2009 minus 1960 is 49 years. So we're going to go point to the home screen, which it already did, and I didn't. Point. Okay. No, I'll look at it a second. 0.229 times 1.03 to the power of 49. Anyone get 0.97? Almost a million people? Okay. Now, did you guys notice that this 0.229 was very close to 0.23 right here? Why wasn't it exactly 0.23? Because isn't this our original starting value? But when it estimates a best fit, okay, it shifted it just a little bit off, and that's why. All right, and estimate when the population will be twice that. We can do this algebraically, or you could do it on the graph. What is twice the 1960 figure going to be? So if we put 0.46 equals 0.229 times 1.03 to the x, first thing we're gonna do is, okay, so 0.46 over 0.229, and then take the log of both sides. And then you'll end up dividing one more time because the x is out in front now. So if you didn't want to have to round anything, it would be log of 0.46 over 0.229, which is ridiculous because we already rounded those numbers, divided by the log of 1.03. And you would have to add that to 1960. Anybody getting a year?
1984.
Anybody else getting 1984?
I round it like all the way through.
83, 84, somewhere in there. I'm not gonna have a heart attack about that. So I'm thinking it's gonna happen sometime during 1983 that it would move past, or by 1984. Anyway, you get the idea. I think we're pretty much done. There's a couple finance menu questions. On the back, we're solving for x. You want to look at worksheet 23A if you need examples of doing all this stuff. Okay, does somebody have a question? Carrie, did you have one you wanted me to go over? 20? If I don't think I really want to rewrite this. Oh, I will. I don't think it's tricky. 2/3 to the 2x equals 4/9, right? If I just rewrote it. This 2 is squaring the 2/3. What would that make it? If I square the 2 and the 3, I'd get 4/9, right? So I have 4/9 to the x, that's supposed to be an x, equals 4/9. So I'm thinking x is 1.
Would it be wrong if I typed that in the calculator and divided by 2?
Should get exactly 1.
Okay. Could you do 27? It's like I get confused with the logic on both sides.
Okay, so you need to combine these two and then rewrite it as an exponent sentence. So adding two logs means they can be combined to one where you are multiplying. And then it's going to be 3 to the 4th equals, and when you multiply those together, you get 27x squared. And you can only keep a positive answer when you get done with all that, okay? Yeah. Somebody else have a question on one? 19? Do you need me to leave that up for a second? Everybody get that? I'm thinking that I just typed this disaster in, like change a base or use your log base thing, and then subtracted 6 and divided by 3. If you don't have a log base on your calculator, you have to do this. But I would get an ugly decimal over here, then subtract 6, divide by 3, all that good algebra stuff, okay? Any other questions? Okay. I would really like you to turn this packet in by the end of the day today and be done. If you can't do that, you can turn it in after break. I know some of you have got a lot of other stuff you need to work on. I'll let that slide. If you would like to pick up the review for the final exam packet, okay? It is up here by the blue basket. If you just want to page through it and say, good grief, I don't remember how to do any of this sequence stuff from chapter 1. But at least you would be reminded of what it is you don't know, so that when it comes time to review in class, you can say, Hoffbauer, chapter 1, we got to go over that, okay? So even if you don't work on the packet, take a couple minutes and look over and go, yeah, I don't remember how to do this at all, okay? We will be finishing up the chapter on logs and exponents when we get back that week. Hope to see you soon, Sierra.